Okay, are we ready to start?
Wait a second, please. Yes, it seems to work. Okay, yeah, please start.
Okay, so so welcome to this session, and I'd like to invite Tom to present his cellular Howe theorem. Thanks.
Okay, thank you. I'll try to share my screen. Is this working?
Yes.
Okay.
Yep.
So the paper is about a cellular Howe theorem, which means theorem about congruence or bisimilarity using an abstract version of Howe's method. Oh, damn. That was unfortunate. Sorry. So the motivation for this is that in programming language research, our results are often stated for one typical language. And the goal is to provide high-level mathematical tools for instead stating them for a whole family of suitable languages. And so the contributions in summary are as follows. We introduce the notion of a Howe context in which we have a notion of signature for programming languages. And also we define there in any Howe context, we can define substitution clause bisimilarity, which in the particular case of call by name lambda calculus instantiates to Abramsky's applicative bisimilarity. And then our main result is that if the language complies with a certain format, then by substitution clause bisimilarity is a congruence. And maybe the most important idea of the paper is that of a co-simulation. So just in 30 seconds, in order to introduce it briefly, that's our definition of a simulation. So the thing is, it's exactly as in the usual clause for simulation. And it says that for all pairs of red arrows there making the square commute, there should exist a pair of green arrows making the remaining squares commute. And so that's saying that R is a simulation from X to Y. And co-simulations are obtained by kind of orthogonality or duality. So we decree that a co-span, like AEB here, is a co-simulation when it satisfies exactly the same lifting property with respect to all simulations R. Right, so that's in 2 minutes, that's all I can say about the paper.
Okay, thanks very much, Tom. We have a question from Slack, but it's from Nathaniel, who I don't know if he's here just now. So let me first ask whether anyone else here has a question for you. I think you can just speak if you've got a question. Okay, so let me come to Nathaniel's question then. I think you already discussed it a bit on Slack. It's just about an hour ago that you've been talking about it, so yeah. I haven't managed to catch up on it yet. Yeah, but the question is whether the results about skew monoidal categories can be interpreted as results about relative monads. Is there anything you want to say about that, Tom? Or?
I can't really add anything to what Ambroise already answered, which is there.
Yeah.
So the answer is yes, basically.
Okay. All right, thanks. Okay, great. So if someone has a question, just shout out. But otherwise, I've got a question trying to get a little bit more intuition. So for me, applicative bisimilarity is a bit strange because you have sort of labels in the semantics which are syntactic. So the syntax and the semantics are not really separate in the semantic notion of bisimilarity as it was set up by in the original work. Whereas your work is very categorical and semantic. So can you say? I mean, can I glimpse where that's coming in this notion of co-simulation or somewhere else in your development?
I think it's coming in before, just in the very definition of how the whole system is set up.
Yeah.
And maybe the trick that you're looking for is that we don't really have labels there.
Right.
We essentially view evaluation as opening the body of lambdas.
Yeah.
So it's a heterogeneous relation. And then we restrict attention to substitution clause relations.
Yeah.
So being a bisimulation is, well, you have to match the evaluation, and then you get to open terms. And by substitution clausedness, you need to be stable under any instantiation.
Right.
Not sure if that answers your question.
Yeah. Okay. So it's those two go together. Yeah. Okay. Thanks. Yeah. Yeah. Okay. Anyone else? Oh, I had another. Okay, I'll ask another question about intuition. So you changed like what the Fiori-Procchincuri idea of strength and functor categories were a little bit. Is it easy to give an intuition why that's sort of necessary? I think you did to some extent in the paper, but why that's sort of necessary? And maybe that's to do with Nathaniel's question. I'm not sure.
No, I don't think it has to do with Nathaniel's question.
Okay.
And I'm not even sure it's necessary. I did it because I couldn't see why how to do it otherwise. Yeah. And the intuition for that is that I needed the monad that models the calculus to be familial. Yeah. Which is a technical property. Yeah. And the usual setting yields non-familial monads. Yeah. But in the last weeks, in the past few weeks, Ambroise has been working quite intensely on this body of work, and I think he's not here, but he would probably tell you that familiarity is not that much necessary in the end.
Oh, okay.
So maybe there'll be some changes in the journal version. We'll see.
Yeah. Okay. Great. Yeah. Okay. All right. Okay.
Thank you.
Well, thanks very much, Tom, for the nice summary and the discussion. Maybe we should move on to Clemens now. Yeah, thanks.
Thank you, Sam. I'm now trying to share my screen.
Okay.
Yeah, our paper, do you hear me? I first have to check.
Yes, yes, I can hear you fine. Yeah.
Thank you very much. Our paper is about a completeness result for 1 free star expressions. And by that, we mean regular expressions generated from a constant 0, letters over an alphabet, over a given alphabet, the possibility to form sums, product, and binary Kleene star. So with unary Kleene star, 1 would be recoverable, but we use binary Kleene star. And we use Milner's process semantics, which gives finite process graphs that he calls charts to star expressions. And for that, he defined a sound proof system in 1984, for which it is still open whether it's complete with respect to bisimilarity under the process interpretation. We are not looking at that system, but we are adapting it to 1 free star expressions. That means we are doing away with axioms that contain 1, and we switch from unary to binary Kleene star. And the main technique for our result is a graph property that we call loop existence and elimination property, which holds for the interpretation of 1 free star expressions. And it's defined by a kind of peeling off procedure of subloop charts that lead finally to charts that do not have an infinite path. Such charts that have the property Lie we call Lie charts. And the main lemma of our proof consists in the statement that the bisimulation collapse of the Lie chart is again a Lie chart. We prove that by a stepwise elimination procedure for pairs of bisimilar but non-identical vertices that preserve this property Lie in each step and finally lead in a Lie preserving way to a bisimulation collapse that has the property Lie. And we've got 2 theorems. The first is expressibility, namely that the chart is expressible by a 1 free star expression modulo bisimilarity, if and only if its bisimulation collapse is a Lie chart. And the second is the completeness of the system BBP, where BBP stands for Bergstra, Bethke, and Ponce, who have studied the system already in the 1990s. And we show that it's sound and complete for bisimilarity under the process interpretation for one free star expression. And basically the idea is to use the bisimulation collapse as an anchor to relate two graphs, two charts that are bisimilar. And that is at the moment all that I can say about our paper in 2 minutes. Thanks.
Okay, thanks very much, Clemens. Oh, by the way, your screen wasn't sharing. That was intentional, wasn't it?
No, that was not intentional.
Oh, sorry. Okay. Is there anything you want to share with us on this?
I would like to share the screen with you, but
oh, it was very clear what you said without the
okay.
Okay.
I'm sorry. That is really. Okay. Then I just want to share the last slide with you. Let's do it again. So
yeah, now we see it.
I'm sorry for that. So here are the two main theorems, expressibility and completeness. And you see here the stepwise procedure of getting to the bisimulation collapse in a Lie property preserving way, which we do by identifying appropriate pairs of bisimilar vertices and then linking one through to the other. That is what I wanted to share.
Okay, yeah, thanks. Okay, so we have a question from Jana. Do you want to ask your question, Jana Hoffman? You have to unmute yourself.
So my question was, this is done for one free star expressions.
Indeed.
So in the end of your talk, you hinted at whether, at how this could be adapted for complete star expressions. And I was asking whether the Lie property would still be the same for that case.
As I answered, thank you, Jana, for the question very much. I just want to explain now to you what the slight and subtle difference in the definition of a loop is. And if I go in the definition of loop in my presentation, then I define the loop charts one with three properties. The first one, that there is an infinite path from the start vertex. The second one, that every infinite path returns to it. And the third one, that termination is not possible. And the third property, that termination is not possible, would have to be changed for the general case into one that I even can show to you, because it is a talk that I gave last Sunday in the term graph workshop. And you see here, I've changed just the last property of a loop to termination is only possible at the start vertex. And then the peeling off process should be entirely the same for one charts as for charts. And at least that is my best hope of getting the ideas also working for the case in which one may occur. And I would encourage you to have perhaps a look at my talk on the term graph workshop, where I gave a little bit more of the background of the situation with one. But thanks very much for the question. It's very, it's absolutely clear. That
Great, thank you.
Okay, are there any more questions, or Jana, if you had a follow-up, feel free to ask.
No, I'm good for now. I can watch the talk, so thank you.
Okay, all right. Oh yes, you haven't had time yet. That was 39 minutes ago.
It is another talk. It's not just the talk, the LICS talk, but it's a talk for a workshop. Yes.
Yeah, sure.
Okay, well, Clemens, thank you very much.
Thank you too. Then I stop sharing to
yes, thank you.
For the next one.
Yeah. Is the next speaker, is it Catalin?
Yes, I'm here.
Okay. Oh,
okay, so I try to see if I can share now my screen, because right before this, I was trying to do this and then I had some problems. Okay, so is this okay? Is the outline appearing to anyone?
Yeah, excellent. Yeah.
Okay, good. Okay, fine. So, our paper that we presented here is a paper about alternative temporal logic, which is a model logic for specifying the existence of group strategies for achieving joint objectives, which may incorporate some temporal aspects as well as other strategic sub-objectives. And establishing a good notion of bisimulation would be a first step towards model theory for this kind of logics. And so the idea behind the bisimulation would be that two histories are related by bisimulation. If two histories are related by some bisimulation for some coalition from some set of agents, then any objective for that coalition which would be satisfiable, which would be achievable in one of the histories, would also be achievable in the bisimilar history. So we focus here. So there's a notion of bisimulation for ATL from the very introduction, but we focus here on an alternating temporal logic with imperfect information, which means that strategies employed by agents must be uniform. So they must prescribe the same action for agents in the two histories that are indistinguishable for that agent. So in this case, we prove a Hennessy-Milner type theorem, which contains two parts. So the correctness part, saying that whenever two histories are bisimilar, then any ATL formula for the coalition for which the bisimulation has been defined, which are satisfiable in one of the histories, is also satisfiable in the second, in the bisimilar history. And the completeness part, which says that whenever two histories satisfy the same set of ATL formulas for some coalition, then they can be related by some bisimulation for that coalition. So the difficult part here is the reverse implication. So the completeness part, for which we define a bisimulation game, actually, which is an extension of the classical bisimulation game. And this bisimulation game is played between 4 players. So we have 2 spoilers and 2 duplicators. One spoiler which is perfectly informed, and the spoiler which is imperfectly informed, has imperfect information. The same structure for the duplicator coalitions. So the spoilers are supposed to prove that there exists a ATL formula which separates 2 histories, while the duplicator's objective is to prove that that any pair of histories actually is related by some bisimulation and satisfy the same set of formula. So the need for the imperfectly informed players comes from the need to have uniform strategies, so that the necessity to have the same strategy prescribe the same action for an agent in 2 histories which are indistinguishable. And we prove that this bisimulation game is determined, and relying on that, we are able to prove the complete path. And the underlying message is also that this bisimulation game cannot work if we only work with agents with spoilers and duplicators having perfect information. We also prove a undecidability theorem saying that this bisimulation cannot be decided. Yeah, so that should be all. Thank you.
Okay, thank you very much. We have a question from Jana again.
Yeah.
Do you want to question, Jana?
Yeah, hi. Thank you, first of all. So I have a question regarding the decidability result or undecidability result. So is there any hope to get into a decidable class by making some assumptions or restrictions, or like how undecidable is that?
Yeah, it's a good question. Thank you. I think that one has to dwell into results for decidable subclasses for alternating temporal logic with imperfect information. So we haven't checked this path, but I would suggest looking at alternative temporal logics for game structures which have a hierarchical information structure between the agents, or maybe broadcasts, or maybe what's these lack of information forks, and this kind of structures. Perhaps they would they exhibit some decidability result for the bisimulation, but that's just a hint. We haven't checked this path.
I see. Thank you.
Thanks. Are there any further questions for Kato? Okay. Well, thanks very much, Katalin, for your summary and
thank you.
Question.
I'll stop sharing.
Thanks.
Okay. I should be okay.
Yeah. Great. So the next speaker or answerer, whatever we're calling this, is Jeremy, who's going to, I think it's you, isn't it, Jeremy, who's going to talk about refinement-based game semantics. I can see he's in the room, but I can't hear him.
Yeah, so he should be around.
I'll be here. I'll be joining in just a sec. Again, my computer is capricious.
Okay.
Apologies for that.
Oh, that's fine. That's fine.
Actually, so I will share my slides briefly to give an overview. So this is work that we come to this from software verification and certified systems. We're working on the Certicos OS kernel, and especially the Deep Spec project is a project that tries to connect together the proofs of correctness of all of these components that I've listed here. And so based on some ideas for certified abstraction layers, which we use in Certicos, we try to develop a game model that's suitable for connecting all of these components together. And to do that, we actually synthesized various approaches. In particular, we use a very simple form of game semantics, which we merged with the refinement calculus, essentially. And so the secret ingredient in the refinement calculus is dual non-determinism, and infinite choice over both angelic and demonic non-determinism, which allows you to express strategies very nicely. And so we sort of re-examined game semantics under that point of view to build our model. So the key insights is that the usual construction of strategies, you can think of it as using angelic non-determinism. And then if you upgrade so that you have both kind of non-determinism and you lift all restrictions on angelic non-determinism, then you get a model that's very expressive. And so so that's the basic idea. We're able to do this combination. We also use ideas from algebraic effects and free monads, things like that, to obtain something that's nice to use and nice to formalize in a proof assistant. And in particular, in the paper, we demonstrate how you can deal with data abstraction in that setting, which is very important in Certicos and in the setting of large certified systems, so that you can shift your point of view from very low level things, your assembly program executing with registers and so on, to high level structures that you want to talk about in much more mathematical terms, so to speak. So I guess that's it.
Thank you very much. Yeah. So I have a question, but Jana has a question. Do you want to go first again, Jana?
Well, yeah, maybe. Thank you. So my question was, so I'm not an expert on refinement calculi. So you said that this could be used in the CompCert compiler. So how would you use it, like going from the abstract to the CompCert compiler? How would you implement it into the compiler? Where would you use it?
Right. So thank you for the question. It's actually quite interesting. The first step for integrating CompCert is that you have to extend CompCert a little bit in the way that compositional CompCert does, for instance, which can be seen as a form of game semantics, so that the external calls and incoming calls of each module are observed explicitly, and you get a semantics that's not just for the whole program, but also for individual program components. And then the way you would encode this in our model, so this is the forms that our strategy takes, so to speak. So here F is the game on the right-hand side, and E is the game on the left-hand side. So for a C module, you would define a game where questions are function calls and answers are the values that the function returns. Then your strategy will tell you how, when you have an incoming question, you're going to do a series of external calls, or maybe record events in your trace that you can express in terms of the game E. And then finally, your function returns. So once you do this, you need to go from this transition system description that you have in CompCert to the strategy description that we describe in the paper. And one interesting aspect of that is actually that if you interpret the non-determinism in CompCert transition systems as angelic, you get the interpretation that corresponds to forward simulation, if you're familiar with the way CompCert is designed. And if you use demonic non-determinism, you get the interpretation that corresponds to backward simulations. And if your transition system is deterministic, then the two results will be equal and the notions of simulation will coincide, roughly speaking.
Okay, yeah, thank you.
Can I follow that up? To what extent have you, because this is a theoretical paper, is that, but to what extent have you, is this being integrated into a verification tool?
Yeah, so we have formalized part of the paper in the Cockproof Assistant. I can post the link to our GitHub repository in the chat if folks are interested.
Okay.
And then we're also working on trying to adapt CompCert and embedding the semantics of CompCert in our model.
Okay, great. Oh, Tom is raising his hand.
Yes, I am. Thank you.
Okay, hi Tom. Yeah.
Hey, I just wanted to ask a naive question from a game semanticist's point of view. The game semantics that you seem to have here is quite primitive compared to AJM games or high-London games. I'm wondering why this is the case and why you don't need more. So perhaps it's just the fact that the language that you're considering isn't high order. Is that the point?
So yeah, I mean, in a traditional game semantics paper, you'd give a language and express the semantics in terms of games. In our case, it's a little bit different because our model, the way we are thinking of using it is as a high-level glue to connect various components of certified systems. And so we only need to model the interactions between the components, so maybe between the kernel and the hardware and things like that. And so it's enough for this application that we have a first order model. And one advantage of this is that it makes the model very simple. So in terms of formalizing it, that makes things easier. We can have this monadic approach to provide a nice interface to it, and so on and so forth, which would be more complicated to do with sophisticated game models. But we could design game models based on the same principles that sort of are more complex, and we could even then embed the model that we present here in a more complex game model. But for application, high order computation is not essential.
Maybe I want to, so this is Zhong Xiao, I'm a co-author of this paper. Maybe I want to add a clarification. So when Jeremy talk about the first order, it means the type is first order, but in most of these large-scale system verification or verification of low-level C programs, even first order can already support things like a first-class code pointer. You can have a pointer pass around, and the game semantics treat those code pointers as interaction with the environment, between system and the environment. So even the first order fragment of gaming semantics is already sufficient to describe a large-scale system composition. And in the 30-course project, we are not only using it for verifying sequential C programs, we are using it to verify concurrent program where we have multiple threads, and each thread is modeled as strategies. And we are, of course, coming from the practical application side and not necessarily developing full-blown game theory and game semantics for higher order functional languages, but more from the application side to see what fragments, what ideas can already have a huge impact on large-scale verification.
Yeah,
Yes,
thanks.
thank you.
Oh, Luca Aceto has a question. Is he here, or Clemens has?
He asked me that by email. Perhaps he's watching the YouTube stream.
Ah, okay.
That's why I posted it.
Okay, thanks. Yeah. So, okay. So Luca Aceto has written automation of the verification ? Compare with the work by Sigurd Bjarnason on nickel. So, yeah. Is there a comparison to nickel or?
Wait, he just said hyperkernel, not nickel. I'm sorry.
Okay.
Yeah, we know both of those papers.
Yeah,
but,
great.
Jeremy, you want to answer, or I should answer?
Yeah, I mean, the kind of work we do is more in interactive proof assistance, like the Coq proof assistant. So we haven't considered applications to model checking and things like that. There may be connections with ATL, for example, that also has this dual non-determinism going on. But.
So Jeremy, these papers are push button verification.
Right.
Using SMT solvers. And I would say, so right now for all these 30-course related project, deep spec related project, we rely on Coq tactic, and sometimes use external SMT solvers to provide the partial automations. And you know, we probably don't have as a high degree of automation as these SMT solver-based projects. However, the main difference is we have the complete proof. That is, you know, you have a main theorem, you have the linkers, you have all these different theorems actually indeed composed and mechanized, you know, and composed to the single proof. Where most of these SMT solver-based automation only show you how to prove different obligations. But when you want to link the high-level theorem together and it involves language, compiler, you know, they don't have those glues. So that's the kind of what I see as the trade-off between, you know, formal verification using a rich proof assistant versus those, you know, based upon SMT solvers.
I can only thank you in the name of Luca Aceto. Thank you very much.
Thank you, Luca.
Do we have any more questions? I wanted to ask briefly. I was intrigued by the way you're using algebraic effects as part of the framework. And I don't think I've seen algebraic effects and game semantics come together. Or maybe I know a couple of pieces of work where that happens, but it seems a bit unusual. So I just wondered where you saw that going, or how, yeah.
Yeah. So algebraic effects are used in interaction trees, for example, which are a model that's very close to our own. And the point is, with these limited forms of plays, that's very similar to what you get if you have a free monad on an effect signature. So we try to sort of synthesize these things, and you can think of the composition of strategy as effect handling, for instance. I don't know if you have more, you want me to be more specific, or?
No, I found that very interesting.
And that's also an advantage of having very simple games, because if you had more sophisticated games, then you would get into, on the algebraic effect side, it would get into multi-sorted signatures, where each sort is the kind of state of your game. So
yeah.
I guess again I want to add there's a interesting connection between certified abstraction layer and the algebra effects, because the certified abstraction layer hides all the private state and encapsulated inside the object.
Yeah.
And if you look at the way we build the OS kernel using 65 layers, you can see each layer is almost like a algebra effect. So, so in that regard, they are connected, and we are still working out whether, you know, we can you know, unify them.
I see. Oh, is that something you've written about in other work, John?
We didn't explicitly explore the relationship, but the idea that algebra effects attempt to hide the, you know, state effects and so on, that's basically pervasive in all the previous paper on certified abstraction layers.
Yeah. Okay, thanks. So if we have no further questions, okay. Well, thank you very much, Jeremy, and for all those questions and answers.
Thank you.
I think our last speaker is Andreas.
Right. Can you hear me?
Yes.
Great. Okay. Let's see.
So,
yeah. Now you can also see.
Excellent. Yeah. Thanks.
Good. Okay. Yeah. Thank you. So, yeah. Thanks for staying around, everyone. My name is Andreas. This is a joint work I did with Umang Mathur and Mahesh Vishwanathan from UIUC. It's on a somewhat different topic. We're studying complexity questions that arise in the analysis of concurrent systems. So the motivation behind concurrencies should be pretty obvious to anyone who has actually programmed and used computer systems today. So the problem we're looking at is data race detection, and this is a very widely studied problem that go back to several decades. There are many different techniques that one can attack this problem. Most techniques are basically dynamic techniques, they fall in the area of dynamic analysis. So instead of analyzing source code as you would do in static techniques, here the idea is that you are observing a program execution, and while you're observing it, you want to perform some analysis on it and decide whether you have found a bug or not. Right? And this has the advantage that typically, because you're observing concrete executions, you can make sound reports of bugs so that you don't overwhelm the programmers with warnings. And they're also fairly lightweight, as opposed to dealing with an undesirable problem of static analysis. So in our setting, we're dealing with shared memory concurrency. So these executions that I illustrated here actually look like this in more detail, where we have a number of threads. In this case, we have just 2. And every thread performs a sequence of actions to shared memory. So it can either acquire a lock or release it. And it can also write to shared memory and communicate with other threads that read from the shared memory. So this is the setting. And as I mentioned, the errors that we're looking at is data races. So data races, in case you're not familiar with, are occur when you have a concurrent execution sigma, where you have a pair of conflicting events that happen at the same time, and they access the same memory location. So perhaps the figure is more informative. On the right, we have 2 threads. They operate concurrently, and here we have the 2 threads accessing the same shared variable x at the same time, and one of them is modifying it. So this is a data race. There are many reasons why you don't want this to happen in your program. So there's a lot of effort into detecting this automatically. Right? So the most naive approach in this setting is to just do dynamic race detection, which means that you're just observing an execution, and then you just keeping track of what the memory accesses are and find out whether you can have 2 that are next to each other and constitute a data race. But these techniques are typically very, very low coverage. Instead, there's a very promising line of work which focuses on prediction. So the idea is that instead of waiting for the data race to manifest in the observed trace, you're going to observe a trace that might be data race free, like the one in the bottom, where these 2 accesses are separated by an intermediate event. But nevertheless, you can infer that there is some valid reordering of this trace that would lead to another valid trace of the program in which you would actually observe a data race. And so this is the data race prediction problem. There has been a lot of practical works in how to do this efficiently, but the fundamentals of the problem, its theory and its complexity had not been studied. So this is what the gap that our work fills. So in one line, the contributions are as follows. So we have the data race prediction problem. The input is a concurrent trace sigma and 2 events that conflict. Sigma is sort of having n events, and we are over k threads. And the question is whether you can find a witness reordering sigma prime, which will expose a data race that was otherwise hidden in your input trace sigma. Right? And so we paint the complexity landscape of this problem. So first we study the general case, and we establish an upper bound of time roughly n to the 2k for n events and k threads. So this is exponential in k, but it becomes polynomial when you only have a few threads. And then approaching this problem from the other direction, we establish a lower bound of W1 hardness on the parameter k, which means that the problem is not only NP hard, but also not likely to be fixed parameter tractable in the number of threads. So essentially, you have to suffer some exponentiation on k. And even further, under the exponential time hypothesis, it follows that we also have a linear dependency on k in the exponent. So in some sense, our upper bound and the lower bound kind of match. And then we go on to examine special cases. And the first special case we examine is when the communication topology of the concurrent program is acyclic. in this case, we saw that you can actually solve the problem much, much faster in pretty much quadratic time in your in the length of the inputs. And again, we also saw that the problem is orthogonal vectors hard, even for just 2 threads, which means that the problem has a conditional quadratic lower bound as well. And so again, we have like matching upper and lower bounds in the case of acyclic communication topologies, which characterizes concurrency like fork join parallelism or a server with clients and so on. And finally, we study a parameterized version of the problem where the parameterization happens with respect to say, a notion of distance between the input trace that you observe and the witness that you are trying to construct. And we saw that, in fact, when the distance is constant, there is a very efficient linear time algorithm that decides whether you can construct such a witness. And I'll stop here. Let me know if you have any questions.
Okay, thank you very much. That was nice and clear. Michaela has a question. It's about your. It talks about slide 4 in your original talk, but I think the same picture was here. Yeah, that's right. Okay, okay. So you know the question. Do you want to ask the question, Michaela?
Yes. So it's pretty much about this picture on the right we see here. This was also on slide 4 on your video, on the talk there. So I was wondering why it is really a data race here, because we are locking in thread 1. So the write axis is locked there, but the read axis in thread 2 is not locked. So is this really a data race? Because if we protect the writing with a lock, do we also have to lock the read on thread 2, or is this really a problem here? I don't get this really.
Right. So strictly speaking, there is no data race in the example in the bottom. But the fact that you have just locked the write access doesn't mean that you're protecting the read access from happening at the same time. Right? For this to be avoided, you would also have to protect the read with a lock, so that the 2 critical sections, so that you indeed have 2 critical sections and they won't overlap. So now in this case, the effect of locking is actually vanished, because no one is from the opposite thread is actually trying to see whether this variable is protected by a lock. They just read.
Okay. Yeah. Good. Thanks.
Okay. Yeah. I mean, just to, so that's sort of coming from your definition of what's an allowed reordering, Andreas. That's right.
Right. Yes. So this is a good question, and let me see. I think I have a slide here. Maybe. I guess I have to go one by one. Right. So which reorderings are allowed? There is a notion of correct reorderings, which precisely captures the kind of orderings that we're allowed to do. And the idea is that by reordering, you have to respect the thread order. So you are not allowed to reorder instructions that are executed locally in its thread. And at the same time, you have to respect the so-called last write property, which means that every read has to observe the same write in the reordered execution as in the input execution. And this is a sound definition in the sense that if you preserve this property of every read observing the same write, you're also guaranteed to take the same control flow locally in every thread, which means that the events that you're exposing to be in arrays are actually events that are actually executed. So yes, overall, there is a notion of correct reordering, which is basically a sound notion, meaning that a correct reordering is guaranteed to be a valid trace of your concurrent program.
But there is no surprise in this slide, so to speak, right? I mean, there's nothing that where you are deviating from what others are doing here, right? Or is this?
So the notion of correct reordering is not a new definition in the paper. This is a standard approach that has been followed also by practitioners. Yes. What was missing was actually what is the complexity of finding whether you can have a correct reordering as compared to your input trace.
Okay, I have a question. Anyone else got a question? At the end of your, I can't remember whether you had it in this talk, but at the main talk, you mentioned randomization and parallelization at the end of your talk briefly. Can you say a bit about what you mean about that?
Okay, let's see if Umang is still here. Umang, do you want to jump in?
Oh, right.
Am I audible?
Oh,
Yes.
right, because you didn't give the talk. I see. Okay.
Yes.
Right, yes.
So let's have Umang answer the question. Thank you.
So, so when you look at these executions, you need to predict whether there is a reordering. Okay, and if you look at practical instances of this problem, they're extremely large. Okay, so when you want to develop practical algorithms, they must be sort of linear or sublinear algorithms. And in the hope of getting sublinear algorithms, it makes sense to come up with to sort of delve into this genre of sampling events in the executions and then determining if there is a reordering.
Randomly sampling, you mean?
Yes, random sampling.
Okay, interesting. Yeah.
Right. So just to add up on that, yes, the goal here would be maybe to even have sublinear time algorithms, because in practice these can be millions of events, like n can be in the order of 10 to the 8 or so.
Yeah.
So we would also be happy if with some probabilistic guarantees that come out of sublinear algorithms.
Well, nice. Yeah. Or even just practical.
Sure, the practical component is strong, actually.
Yeah. Yeah. I mean, another thing you said in your talk was that I think you said 12 papers a year are being published at the moment.
That's right.
Is this going to change now?
So I don't think that's going to change, because the results of this paper are in some sense encouraging, because the same trend in fact can continue. But at the same time, coming up with a sound and complete algorithm is still going to be a problem. So I think papers will keep coming up. I think so. And also, data risk prediction is one problem. There are many other problems of the same flavor that are not known to be efficiently solvable.
Yeah. Thanks. Okay, do we have any more questions? Okay. Okay. Well, thank you very much, Andreas and Umang.
Thank you.
And yeah, thank you to everyone in this session. But let me just give a couple of minutes in case, or a couple of seconds, in case anyone's got a question for another speaker from this session that they thought of a question for, but perhaps not. No? Okay. Well, the Slack's open if anyone wants to discuss things further there. Yeah. Okay. Well, thanks very much then. Thanks.
Thank you.
Thank you, everyone.
Thanks.
Thanks. Thank you, everyone. Thank you.
So langsam. We should be at the end at the YouTube stream now too, because there is a delay. And I can close the meeting now, I guess. Okay.
Unless Lijun wants to talk to me. Lijun, you want to? I don't know. Hi.
Hi, Lijun.
Anything to discuss? You're also in the office.